Hello everyone. In this video we are going to be discussing a couple of the methods through which we find the volume of a solid that is obtained by rotating a region enclosed by some functions about a given axis, and in this problem in particular we have these functions, so we're going to find the volume of a figure generated by those functions that is revolved around the x-axis first, and then we're going to talk about the y-axis. And hopefully that'll generate a good discussion about the differences in those two processes and the different types of things that we need to be aware of and all that. So let's go ahead and get started. Of course, for all of these problems, despite whether it's disk method, washer method, or shell method, our first step is going to be drawing the functions given to us and identifying that area that is being enclosed by all the functions, right? So let's start with that. Let's go ahead and sketch y equals square root of x minus 2. And hopefully we know that that is just y equals square root x moved over 2 units to the right. Looks something like that. Let's just call that f of x. And we have x equal to 6, so let's say that 6 is somewhere over here maybe. So here's that vertical line. And of course we have y equal to 0, which is just the x-axis. Okay, there you go. All right. So, of course, the first thing we want to do is identify that region enclosed, like I said. And the reason we do this, the reason it's so important to sketch the graph and identify this region, is because it helps us to figure out which method of integration we're going to be using, right? Because there's disk method, there's washer method, and there's shell method. And for each of those methods, not only does the figure look different that is revolved around the axis, but also there's a different formula for each method, right? And the sketch helps us to identify the components of those formulas. So let's go ahead and identify which method we need to be using. And so I like to just shade in the area that's being enclosed, and then we can draw kind of the figure of that is being generated by revolving that area around the axis. And we can see that when we do this, there's no gap, right, in the figure. There's no hole in the middle. So what that means is that we're just going to be doing disk method. If there was a hole in the middle, that would be a washer method, but it's very connected. So that means we only have one radius. So now that we've identified its disk method, then we have a particular formula for that volume, right? So we have integral from a to b of the radius of the disk squared times dr. So our next step is just to find the components of that function, right, that equation, which we can use the sketch to help us do that. So what is radius then, right? What are our limits of integration? And do we need to be integrating with respect to x or y? That's what dr is. Should we have our function in terms of x or in terms of y, right? Okay, and so in order to figure out whether or not it's dx or dy, what I like to do is I draw a typical rectangle. And so we know that for disk method and for washer method, the rectangle is perpendicular to axis of rotation. That's super duper important because this rectangle helps us to identify whether or not it's with respect to x or with respect to y. So we draw this rectangle in the area that was enclosed by the functions and perpendicular to the axis of rotation, and we get something that looks like this, right? Okay, so now that thickness of the rectangle is what helps us to find out if it's dx or dy. And so hopefully we see that the thickness is a difference in x values, right? It's left to right, so that means delta x. And delta x, of course, and when we consider integrating this, is going to be dx, turns into dx. So we know that we need our function in terms of x. And luckily for us, we are given our function in terms of x, right? And remember, also the radius is the distance from the axis of rotation, in this case the x-axis, to the function, right? So we have this little blue part representing the radius here, which is just the length of the rectangle. And of course we see that it's the value of that blue mark, the value of the length of the rectangle is just the value of the function, right? So as we move from left to right, the length of the rectangle changes, or the radius changes, and it's modeled by square root of x minus 2. Okay, so there's no need to change that at all. It's already given to us in terms of x, so we just plug that into our function for radius, square root of x minus 2 squared. Okay. Now we need to identify our limits of integration, right? And they should be in terms of x because we have dx here. If it was dy, it would be in terms of y. So hopefully we see that we start at 2 over here. So we start at a equals 2. And of course, we end at 6, so b equals 6. And now we have identified all the components of our formula. And now we just integrate, right? That was the hard part, figuring out all those components, figuring out the method of integration, which the sketch really helps us with. So it's very important to sketch it, to identify that region enclosed, to draw the rectangle, to fill out all of the missing parts of that formula. So now we're just going to integrate. So we have v equals integral 2 to 6 of x minus 2, because the square root of x minus 2 squared is just x minus 2, right? dx. And like I said, this is the easy part now. So the integral of this is x squared over 2 minus 2x. That's evaluated from 2 to 6. So we plug 6 in, and we're going to get, oh, I forgot the pi, my bad. Let's not forget pi here. There is a pi in the formula. I'm sorry. Here we go. Not a big deal here. It's just part of the formula that I forgot. So it's going to be pi times all that. Okay. So we have pi times 36 over 2 minus 12, right? And that's the first part, minus evaluated at the second part, which is 2. 4 over 2 minus 4. All right, so that is going to be pi times 36 minus 24 over 2 minus 4 minus 8 over 2. And that's going to give us pi times, so that's 6 minus negative 2, which is 8 pi, right? And that's it. So don't forget that pi in the formula, right? Don't forget that like I did, and you'll be just fine. So let's see what the difference is when we rotate this about the y-axis instead. So we have the same function, the same functions, the same region that is enclosed by those functions, right? In yellow here, that's what that region is. But this time we're going to rotate that about the y-axis. So again, let's draw what the figure might look like on the opposite end here. We have these two functions here. Let's say this is x equals negative 6. And then here's the opposite side of that figure. Now, what we have here is a gap between the two sides, right? So that is a big indicator for washer method. So now we've drawn our sketch, we've identified a washer method, and of course we have a formula for washer method, right? So v equals, let's not forget pi again, pi times integral a to b of outer radius. So you've seen different variations of this formula, but it's the same thing. So just the outer function or outer radius squared minus inner radius squared times dr. So now we have to identify, again, whether or not it's dx or dy, and then the two functions here, and of course our limits of integration, and then we integrate. So let's work on that. First of all, let's draw our rectangle just like last time. And again, it's going to be within the region enclosed by the functions and perpendicular to the axis of rotation. So we have a horizontal rectangle now, which means that its thickness is determined by a difference in y values, right? So it's going to be delta y, which means that our formula is going to have dy in it. So now let's look at the formula that was given to us, the function given to us, and that is y equals square root of x minus 2, right? And now we need to rewrite that in terms of y, x in terms of y. So let's square both sides. We get y squared equals x minus 2. and then I'm going to bring it up to the right here, and we get y squared plus 2 equals x. Right? So that's a new function that we use. So we just need to do that because we have dy in our integral. Okay, so now let's identify our inner and outer radii. So like I said before, the inner and outer radii is the distance from the axis of rotation to the functions that were given, right? So in this case, we have one radii here from x equals 6 to the y-axis, and we have the second one from the y-axis to our function. So of course, that green line, that has a distance of 6, right? The blue line we just found has a distance of y squared plus 2, right? And it should make sense that it's this, for example, is determined by x equals 6, right? Because the length of the rectangle is determined by a difference in x values. So the length of the rectangle, the radii, they're all connected. So hopefully we see how we get these values for the inner and outer radii here. So let me just write that over here. We have inner radii equal to y squared plus 2, and our outer radii, outer radius, I should say, is just 6, right? Okay. And of course, the inner radius is the one that is shorter, right? And the outer radius is the one that is longer. So it helps me to draw out the radii like I did here. Okay, now let's identify the limits of integration, right? Which we should expect should be in terms of y. So hopefully we see that we start at y equals 0 here, and then going up to this value right here. So how do we find that value? Well, we could set the two functions equal to each other. We could say y squared plus 2 equals 6. Or we could notice that here we have x equals 6, and we could just plug that directly into our function and find the y value. But let's just go with that first method because it's more applicable to different kinds of problems. So we set the two functions equal to each other. We get y squared equals 4 and y equals plus or minus 2. But of course we see that we have a positive 2 here. That's not negative 2. So we can just say that b is equal to 2. And this is a. And there we go. So now I'm just going to erase this so I have some room. Now that we have identified all the components, we can rewrite this formula for this specific problem. We have pi times the integral from, 0 to 2 of the outer radius squared. We said that was y squared plus 2, right? Y squared plus, oh no, that's the inner radius, my bad. The outer radius is going to be just 6 squared minus y squared plus 2 squared. Okay, and again, this is the easy part. Now we just integrate. So v equals pi times the integral from 2 to 6 of 36 minus y to the 4 plus 4y squared plus 4 all dy. So we have, oh no, I put 2 to 6 there. That's from the last part of the problem. This is 0 to 2. So 0 to 2. Pi times, and I'm just going to integrate this now because that's just a bunch of individual terms. So we're going to split up the integral, and we have 6y minus y to the 5th over 5 minus 4y cubed over 3 plus 4y evaluated from 0 to 2, right? So I just distributed the negative there. I forgot to distribute it to this last term. There we go. And now we have the antiderivative of that expression, and now we just evaluate it at the endpoints. So we're going to get pi times 12 minus, I believe 2 to the 5th is 32 over 5 minus, that's another 32 over 3, 4 times 8 here, because 2 cubed is 8, and minus 8. So whatever that is simplified is our volume of the solid that is generated by rotating the yellow region around the y-axis. So hopefully we have a good idea, a good understanding of identifying dx or dy, and the inner and outer radii, and the method of integration we need to use. So that's this video. Hope you enjoyed.